This is Lab 4 Oscillations by Sujit Munigadi. The purpose of this experiment is to find a computational model for a spring mass system that oscillates in two dimensions. For this experiment, we had to, or no, for the model, we had to use the momentum principle and the energy principle, mainly just the velocity update and the position update formulas, and then for the energy principle, the total energies the total energy that equals zero, and the kinetic energy, potential and spring potential energy, and the gravitational potential energy. Uh, for the experiment, we were given that the stretched length of the spring was 0.7 meters, the mass of the ball at the end was 0.42 kilograms, and then using tracker data, the initial position before being let go was at negative 0.114 meters, no, negative 0.114, comma, negative 0.636, comma, 0 meters, and there was no initial velocity. We also had to use two additional formulas in order to find the spring constant and the unstretched L naught value. Uh, the period of oscillation, or t, can be set to equal to 2 pi times the square root of m over k. And since we were given t through tracker and then the mass which was given, we can plug in the values in order to find k, which is just 6.88 Newton meters. And the second formula to find L naught, since we're only looking at the gravitational force and spring force, I set mg equal to ks, where s is equal to L minus L naught, and plugging in values again gets you 0.127 meters for the unstretched length. So here's the video that I had to use for tracker. And as you can see, it just oscillates between in a like elliptical type oscillation, and the x and y values will oscillate throughout. And then here is my GLOWSCRIPT output. And as you can see, the position values, they're closely similar. The red is the experiment and then blue is the model. And the small difference can be attributed to the fact that the actual experiment had other forces accounted for, such as drag and air resistance, while the model only accounted for gravitation. Uh, in order to get that output, we had to set some constants and initial values. We were given the mass of the ball, and then the position and velocity can be gathered from tracker. The gravitation constant is 9.8, the spring constant is 6.88, relaxed length is 0.127. L can just be found by the position of the ball minus the spring position. L hat is just the unit vector of that, and then S is the difference between stretched and unstretched. And then the formulas for the system energies is just K equals 1/2 mv squared, gravitation is equal to mass of the ball times G times height, spring potential is just 1/2 Ks squared, and then the total energy is set to 0. Uh, the And then after this, you just define the initial energies as each variable, and then force gravity and force spring is the only forces that we're looking at. We also apply the momentum principle with the velocity and position update formulas, and then you update the spring with those same three lines. Then for updating the energy, it's just the same values from before, except now for the delta values, it's just the current minus initial value. For the prediction discussion, the energy principle is satisfied, and this can be seen in the graph because the total energy stays at 0, and the other energies, when added together, cancel out. Uh, in the x position, after 3 periods of oscillation, you get a time of 4.843 seconds, which, after divided by 3, nets an average oscillation time of 1.614 seconds. And then in the Y position data, after 3 periods of oscillation, you get a time of 4.558 seconds, which after divided by 3 equals 1.519 seconds. The small difference in time can be attributed to the difference in the way the data was collected, since they were collected in different dimensions. The X is just from left to right, while the Y is from top to bottom.